Yeah, so we have been discussing basics of quantum mechanics, and in the last class we have discussed photoelectric effect, and we have seen that how Einstein explained photoelectric effect, considering that photon or the light is made of particle. Okay, and then we have seen that de Broglie extended that concept and uh, proposed that not only photon or not only light, all matters um, will have wave, okay, associated with it. Now this and he and the relationship he proposed between this matter wave, the wavelength of this matter wave, okay, is Planck's constant. Lambda is Planck's constant over uh, momentum, okay, momentum of the particle. So this was his proposition, and later on we found that uh, Davish and Jarmer performed an experiment. In that experiment, what they did, they used a nickel crystal. In fact, the Davish and Jarmer experiment was not to prove de Broglie's hypothesis, but uh, they were studying the interaction of electron on crystal surface, okay, with crystal surface. So they uh, generate electron uh, by heating up a coil, and they pass uh, that electron, they bombard on nickel crystal, highly polished nickel crystal, okay, um, and they accelerate those electron using a acceleration potential of 54 volt, and their initial perception was that as electron is very tiny particle, even if the nickel crystal surface is very smooth, um, but to electron it is not smooth enough, so electron should scatter in all over the place, and if they manage to detect electron or the current because of electron, um, then they will get a diffuse nature of scattered electrons, right, because they will scatter all over the place. But uh, surprisingly they found that there is a peak, specific, so say this is their detector, okay, and they found that there is a peak at a particular angle that is at 50 degree, okay. Now uh, so they managed to explain this phenomena using Bragg's experiment. Uh, so this experiment was done around 1927, but Bragg studied lot of crystals using X-ray. Okay, the reason he used X-ray, we will probably discuss Bragg's experiment later on in much more detail when we will talk about XR, the X-ray diffraction spectroscopy measurement technique. Then we will discuss about Bragg experiment, but let me briefly tell you, in Bragg's experiment, Bragg used X-ray to study the crystalline planes. Okay, the reason he used X-ray because X-ray wavelength and the distance between crystalline planes are of the similar order. Okay, so what Bragg did, so these are different crystalline planes, okay, of a particular crystal, and Bragg use X-ray. So the X-ray incident on a crystalline plane, it reflected back, and it's basically reflected back from different crystalline planes. Okay, and he found that he is getting diffraction patterns. So diffraction pattern means patterns with high intensity and low intensity light. Okay, those who know diffraction understand what I am talking about. And these diffraction patterns he got, and this high intensity diffraction peak you will get when these lights they march, uh, in the same phase. Okay, when they meet in the screen, if you put a screen or a detector, if they meet in the same at the same phase, then we will get maxima, right? So it is possible to show, or Bragg showed that if this equation is valid, what is 2d sine theta? 2d sine theta is if this is theta, this is also theta. So these are crystalline planes. Okay, so these are crystalline planes. Now, so this second ray, what is the extra path it covered compared to first ray? This if you take perpendicular like this, and if this is the d, that is the distance between two adjacent crystalline planes. Okay, and if this is the perpendicular from this point, then this additional path, this second ray to compare to the first ray. Okay, so if this is d, sorry, my drawing is not good. If this is d, then it is possible to show this is d sine theta and this is also d sine theta. So 2d sine theta, this is the additional path, the second x-ray to compare to the first x-ray. If it is equal to n lambda or lambda, if we so this is order of maxima, because there will be different orders of maxima. If we consider n equal to 1, then 2d sine theta equal to lambda if we talk about first order maxima. So this relation, these x-rays, reflected x-rays should uh, have, so that they can form constructive interference in the form of diffraction, right? Now, so using this, Bragg studied lot of different crystals. In fact, he also studied nickel. Okay, fortunately he studied nickel. So it's much before than this Davison-Germer experiment happened. So if so, so this is say phi, because here also you see electron incident on the main nickel surface and going reflecting back, and this angle we are assuming phi. So here also it is phi, right? So what Davison and Germer did, they tried to explain their finding using Bragg's law. Okay, so if we put phi is equal to 50 degree here, the theta, so all they are trying to do, they are trying to find out if what is the, if there is any wave associated with this electron, and if that is the case, what is the wavelength of that electron. Okay, right? Because according to de Broglie's hypothesis, all matter waves will have uh, all matters will have waves associated with it, and its wavelength can be find out by using this formula. So all Davison and German was trying, they tried to figure out by putting this value of phi here, and they already know the d, that is the distance between two crystalline plane from earlier Bragg's experiment. Okay, so what they did, they put phi equal to 50 degree. Okay, and it was by that time well known that in case of nickel, okay, the particular crystalline plane they were studying, the distance between that crystalline plane, adjacent distance is 0.091 nanometer. Okay, so if you find out 2d sine theta, which is 2 into 0.091 into sine theta is 65 degree, because 2 theta plus phi is 180. Okay, so this is theta, and this is phi. 2 theta plus phi is equal to 180 degree, and phi we know 50 degree, because the phi the angle at which they got maxima is 50 degree, Davison and Jarman. So they put that value, and so they got theta equal to 65 degree. Okay, so if sine 65, so that way they are getting 1.65 angstrom. Okay, because this is nothing but lambda. If you consider the first order maxima, 2d sine theta is equal to lambda, and that lambda value is 1.65 angstrom. So now what they did, they use de Broglie's proposition. So what was de Broglie's proposition? De Broglie's proposition was that lambda is equal to h over p. Okay, and this can be modified a little bit by carefully taking into consideration this, taking into account or multiplying it with c both on the top and the bottom, numerator and denominator. So you see that we already discussed HC. HC is nothing but 1240 nanometer electron volt. Okay, please remember this value. Okay, HC is 1240 nanometer electron volt, and PC. So this PC can be find out in the form of kinetic energy, right? Because kinetic energy is known in their experiment. What is the kinetic energy? You see, they have applied 54 volt accelerating voltage, right? So you can find out kinetic energy. So if you write this PC in the form of kinetic energy, because the momentum is not known, right? So this if you find out and replace this in the form of kinetic energy, that will be really useful. So what is the kinetic energy of the electron? Okay, which is basically bombarding on the metal surface. So this kinetic energy is half mv square. Okay, so you can write in the form of momentum, right? So p square over 2m. So again you can multiply with c in both numerator and denominator with c square, you get this. So PC is 2mc square multiplied by kinetic energy. So if you use this value here, okay, you will get lambda is equal to 1240 nanometer electron volt over 2m c square kinetic energy. Okay, and please check that this mc square, if you calculate separately, m is the mass of the electron and c is the velocity of light, it is possible to show this is equal to 0.511 mega electron volt. And what is kinetic energy? Kinetic energy is 54 electron volt, right? And this comes out 1.67 angstrom. So you see, this is the lambda associated with electron. Okay, and if you take the values of phi 50 degree and put it in 2d sine theta equal to lambda, you get 1.65 angstrom. So these two wavelengths are very close. Okay, and they managed to show that because of the wave nature of electron, they got a peak at 50 degree, right? So this is the first experimental proof of de Broglie's hypothesis. Okay, for this in 1937, Davison and Thomson got Nobel Prize. Now the thing is, please note here that, let me write it once more. So lambda of matter wave is equal to 1240 nanometer electron volt root over 2mc square multiplied by kinetic energy. So if the mass of the particle or mass of the matter we are looking at, okay, if it is large, your lambda will be small, okay, and also if the kinetic energy of the particle, okay, is large, your lambda will be small. So if I try to calculate a large mass, for example, say if I don't know, if we talk about some moving objects which is quite large compared to that of electron, then you see the wave associated with it will be very tiny, right? And it is very difficult to measure in that case. And that is also true in case of if their kinetic energy is large, right? Now, let this part we briefly or very quickly discussed in the last class, so I thought I just repeat it once more in case you have any doubt. Now the thing is, uh, the next thing we would like to discuss is Schrodinger equation. So we all know about Newton's laws of motion, okay? Newton's laws of motion, according to Newton's laws of motion, you know, according to Newton's laws of motion, um, m dv dt or m d2x dt square equal to force, right? And any particular um, time, if you know the position of the particle and momentum of the particle, then it is possible according to Newton's law to find out its position and momentum at a future time, right? Quite accurately. So that's basically Newton's laws of motion. So what Schrodinger tried to do, he tried to develop an equation which basically will govern or which will tell about de Broglie's matter wave. Okay, so seeing Newton's laws of motion, Schrodinger tried to develop equations which will basically describe de Broglie's matter wave, right? So this is in classical mechanics, but soon we found that this Schrodinger equation is bit different compared to that of the mechanics we have been familiar with. So that is the classical mechanics. So this new branch of mechanics came to know later on as quantum mechanics, right? Now what he tried to do, he tried to consider, as it is a wave, he tried to consider, he tried to look at classical waves, how we are representing classical waves, okay? So from Newton's law, we already know that how we represent a classical wave. For example, I have a string, okay, fastened between 2 points. I have a string, okay. So if there is a wave in the string, right, it will say if it is fastened at the two ends. What I am describing, I am trying to tell you how Schrodinger's equation evolved. Okay, there is no proof of Schrodinger equation because it is a fundamental one, such as that Newton's laws of motion. There is no proof, but you use those law to find out that loss of a lot of classical things can be explained, can be measured very accurately if you know at a particular time the position and the momentum of a particle. Okay, so then or position or momentum of an object, you can find very accurately its position and momentum at a future time. So that is how this Newton's law evolved. But Newton's law, there is no proof that how it is coming. This is how it is coming as Newton's law. Similarly, Schrodinger equation doesn't have any direct proof, but you see how it we can describe how it evolves, right? So Schrodinger look at the classical waves. So say for example, I have a string and the string is fastened at the two ends, and I generate a standing wave in the string. Okay, say I have this is my y, this is my x. Okay, uh, so the standard wave equation of such a string can be written like this. Probably you know like these things, but just let me just mention this once more. So this is how the how we can represent say transverse wave propagates along a string. V square d2y dx2 is equal to d2y over dt2. Okay, so this is y, that is the amplitude of the wave, and x is the same direction in the this way, that is where 2 points is fastened. Okay, and this wave not only is changing with x, that but it is also is a function of time, right? So this is how we represents the differential wave equation associated with the string, and you can solve, and of course v is the velocity of the wave, right? And you can solve this equation to find out the solution. What will be the solution? Say a sin kx minus omega t. What is k? K is wave number, you remember? So that is number of waves in space, you can say, and this is frequency, which again you can represent as 2 pi over t. So that is the number of wave in time domain. So this is like a space domain, this is like a time domain. Okay, so this is k is the wave number and omega is the frequency. So this is the solution of your wave which is generated in the stream, right? This is very well known. Now we can talk about similar examples. For example, electromagnetic wave, right? Light wave. So there is electric field, magnetic field. You can say electric field. Okay, similarly you can write so you see these equations look similar, right? C square, that is the velocity of light, d2e dx2 equal to d2e over dt2. And again you can find out I mean we can write the solution in a similar form, right? And of course you can write in the form of using the vector notation as well, right? And so on. So similarly you can write magnetic field associated with this electromagnetic wave, and so on and so forth. So you see this is the solution. Okay, and this is the differential equation associated with any classical wave. Okay, you can of course generalize the formula here and write a to the power I kx minus omega t, something like that, right? So Schrodinger observed this these equations. So and he proposed the corresponding wave function, okay, uh, which is associated with a matter wave. Okay, what is that wave function he proposed? So same expression, same equation. Okay, psi equal to psi, capital Psi equal to a e to the power I kx minus omega t. Right? If you write in the e to the power form, it will be easier to differentiate, easier to calculate and all that. But they are same, you see. Okay, so he proposed that the wave associated with a matter will have similar expression, which is say psi xt. This is capital Psi I am writing, equal to a e to the power I kx minus omega t. Right? So what he did, he basically, as I said, it is a fundamental equation. So it doesn't he doesn't use other equations to derive the corresponding differential equation associated with matter wave, right? So he is assuming this and trying to reach here, trying to reach differential equation. Now all he did, he used conservation of energy. Okay, so how it goes, let's see. So he took derivative with respect to time. Okay, one is derivative with respect to time, because you see one part is with respect to time and one part is with respect to space, right? So with respect to time, so if you do del psi del t of this equation, you will get minus I omega a e to the power I kx minus omega t, and which is nothing but I omega psi. Okay, and you can then he multiplied with I h psi. The reason will be clearer why he multiplied with I h psi later on. So because I h psi will give you, if you multiply this with I h psi, you will get energy, right? H line omega psi, right? Because I and minus I, then minus I square, which is nothing but plus 1, and it is nothing but H nu psi, which is E psi. E is the total energy of the particle, you see, right? According to Einstein equation, E is equal to H nu, that is the uh, energy of the photon or energy of the particle, right? And h line is h by 2 pi. H line is h by 2 pi and omega by 2 pi, you can write this. So because omega is equal to 2 pi by t and omega by 2 pi, you can write nu, right? Nu is the frequency. So this is one expression, right? What about the other one? Other one is derivative with respect to x. Okay, so if you take derivative of equation 1 with respect to x, you will get uh, del psi del x, that is I ka e to the power I kx minus omega t, right, is equal to I k psi. You take another second order derivative of this. Okay, so that will give you ik, and then there is another ik a to the power I kx minus omega t, so that's nothing but k square psi. Okay, So this is say 3, equation number 3, this is equation number 4. So we can multiply this with h line square over 2m. So you multiply with minus h line square over 2m del 2 psi del x2 is equal to h line square k square over 2m psi, that is p square over 2m psi. Okay, because h line k is p. You remember we so this is from de Broglie's equation, lambda is equal to h over momentum, and you can write 2 pi h line over p. Okay, and because h line equal to h over 2 pi, so I am writing in the form of h line, so 2 pi over h pi, 2 pi h line over p. So p can be written as 2 pi h line over lambda, and that is nothing but h line k. So this h line k I am substituting by p here, you see. So this is my equation number 5, right? Now if I use the conservation of energy, okay, conservation of energy is total energy is equal to kinetic energy plus potential energy. What is kinetic energy? Why he has multiplied with minus h line square over 2m? Because this is nothing but, you see, this is nothing but kinetic energy. E square over 2m is nothing but kinetic energy, right? If you take half mv square, that will come out p square over 2m. You remember at the beginning of today's class we had this relation, right? You see, kinetic energy is p square over 2m, right? Half mv square, half mv square, and then you multiply with m, numerator and denominator, and then it becomes p square over 2m. So that is why he multiplied minus h square over 2m to get the kinetic energy part in the equation. So now if you use conservation of energy, okay, what is conservation of energy? Conservation of energy is total energy equal to kinetic energy plus potential energy. Okay, so this is my potential energy part, potential energy of the particle, and this is the kinetic energy of the particle. Okay, so this is the total energy. So from Einstein's relation, we know that E is equal to h nu or h line omega. So that is we can write h square k square over 2m plus u, right? Now, so we can multiply psi in both sides. Okay, if we multiply psi in both sides, so if we use equation 2, what is equation 2? Equation 2, you remember equation 2 is nothing but the total energy. Total energy is, that is I h line del psi over del t. Okay. So equation 2, if you use, from equation 2, that is I h line del psi over del t, okay, equal to energy. So that is nothing but, because, and we know energy is h line square k square over 2m plus u psi, right? So this is the equation, Schrodinger equation. So let me just Let me just arrange it little bit. Minus h line square over 2m del 2 psi del x2, and psi is, we are assuming psi is function of x and t. In fact, psi will be three dimensional, okay, but for the time being I am just assuming it is just function of x and t plus ux psi xt, okay, is equal to ih line del psi del t, right. So this is the final expression of Schrodinger equation. So this is the kinetic energy part, okay, this is the potential energy part, and this is nothing but total energy. So if I just go through once more whatever I have discussed just now. So he looked at classical wave equations, right, solution of classical wave equations. So he considered similar wave equation. I mean, you can take a sine kx minus omega t or a cos kx minus omega t, that is also fine, okay, similar like this, but it will be easier if you take a e to the power I kx minus omega t to do these calculations, okay. So what he did, he find out, all he tried to do is he tried to come up with a similar differential equation as classical equations, okay. So he take derivative with respect to time, okay, and found that it is nothing but equal to total energy. So also he took derivative with respect to x, and if you took del 2 psi del x2, you will find out that it is nothing but k square psi, and you can adjust a bit to come up with it is nothing but the associated with kinetic energy of the particle, okay. So all he did, he used the conservation of energy and equate those two. So that ultimately will give you this expression where this is the kinetic energy, this is the potential energy, and this is the total energy, right. Now this if we, I mean, we will in this particular course we will not go through in very much detail and talk about Heisenberg's uncertainty principle and lot of things about psi and all that, because we will not get time. If you are interested, you can go through any standard quantum mechanics book, for example Varma's book, and any other book, modern quantum mechanics or modern physics, that will cover these basics part of quantum mechanics, okay. And also you can go through additional stuff like Heisenberg's principle or so that you have you can improve the knowledge in that direction, but in this direction. But the thing is, for the sake of time, we are basically not discussing Heisenberg's uncertainty principle. What I just briefly want to tell you, this psi is not exactly same that of xt, okay. You see, we are habituated with xt is the position of a particle in classical mechanics, right. In classical mechanics, in Newtonian mechanics, what we do, as I told you already, if we know the value of x at a time, say time equal to 0 or t1 whatever, right, we can find out the position of x, position of the particle at a later time, say t equal to t2, okay. And also we can find out momentum associated with the particle very accurately from Newton's second law, right, laws of mechanics. Now the thing is, it is not the case, people found that it is not the case in case of this Schrodinger equation. Why? How? I mean, this is because it is not possible to accurately measure position and momentum of the particle at a given time. Okay, it's not possible to measure accurately. Okay, and if you can't do that, this equation will not give you the position or momentum of the particle, I mean the wave associated with the particle at a later stage, okay, because the initial stage will not define properly. Now because this the fallacy is, let me just briefly mention this. Say when we talk about particle is localized at a point, okay, but when we talk about a wave is not localized a point. Wave is like a spread, is spread in space, right? So it is a function of x and at a given time t. Now the thing is, how then it will give you it will give you information. So instead of psi xt, what is more interesting, because psi can be positive, psi can be negative. What is more interesting, because you see, an electron might be there, okay, or electron might not be there in a particular at a particular position and a particular time. But what is important, if we can find out the probability of finding the electron within that waveform, okay. So the probability is more important than finding out the psi. And the way you in this complex wave function, the way you find the probability, okay, is finding out finding this, okay. This is again come from the scientist Max Born, who found that the instead of psi, it is better if we can find psi star. That is nothing but this, okay. If we find psi star, that is the probability of finding the electron. So we can't say that psi is 20%, okay, because or psi is 30%, psi is 40%, because electron can be at a particular place or it cannot be a particular place. So it's like 0 and 1, okay. It can't be between 0 and 1. So it can't be like 20%, 30%, 40%. But what we can definitely say, that probability of finding the electron, okay. So if you do an experiment and if you perform the experiment to finding out the electron at a particular position and time for several instances, and that way you can find out probability, and from the probability can be in the percentage form, okay. But the psi can't be, okay. Psi is an event and it can't be like in between 0 and 1, right? So it turns out later on that instead of psi star or is more important parameter, and this is the probability of finding the particle, okay, at x at a time t, right? Now say this psi square is something like this, okay. Now this is I am plotting with respect to x. So this is the probability of finding the particle. Now if I am interested to find the particle at a particular instant between A and B, the way we do that is taking the area under the curve, okay. So probability of finding the particle, the way we do that, so this is the probability of finding the particle. Now you see in this particular case probability is maximum here and maybe minimum here, okay. Now this is kind of fallacy in a sense ki it is a statistical interpretation, and it gives you some indeterminacy, okay. It can't tell you for sure where the particle is at a particular time, right? So all it will give you is an information of what is the probability of the particle will be there at that time, okay. It can't tell you for certain, for sure. Now the thing is, this is extremely ambiguous, and this ambiguity is still there today. Okay, and people doesn't know whether it is the law of nature, or it is the fallacy in the theory which basically doesn't allow us to find the position and the momentum of the particle at a particular time, right? So with this, I am just I mean, I don't want to go in this direction, but there are a lot of stuff in the web and on the book. If you want to understand more about shy, the only thing, as I said, like, it is ambiguous, and it is people still even today do not know whether it is the law of the nature that we will not be able to find the position and the position of the particle at a particular time, or it is the fallacy in the theory, shortcoming of the theory, which basically not allowing us to find out the particle position and momentum, right? Now there are different properties of psi. Just let me briefly mention those. One is psi star dx. This is must be finite, right? Probability can't be infinite, right? Must be finite and non-zero. And if the particle is there, it can't be non-zero, right? It can't be zero, right? So it is non-zero and finite. Another thing is, you see in the Schrodinger equation, there is del 2 psi del x2. Okay, del 2 psi del x2 term is there. So what it means is psi del x must be continuous. Okay, and psi x and psi xt must be continuous, right? So because if they are not continuous, then the second order derivative will diverge, will give you infinite, will give you infinity, right? So that's not possible. So from the wave equation, you see that psi xt should be continuous, and del psi del x should be continuous, right? And also this probability function, probability should be finite and non-zero. Okay, if there is a particle. Now the thing is, we can carry out the discussion bit more, uh, because all we are trying to do, we are trying to solve this equation. We are trying to solve the Schrodinger equation the way we did in case of classical mechanics also. Say in case of classical mechanics, we had this Newtonian equation and we solve and get this. Here also, all we will try is try to solve this equation for a particular boundary condition. Okay, for a particular situation, and find out psi, because if we can find out psi, we can find out psi star, right? So the ultimate goal is, this is the Schrodinger equation. We use this equation and use boundary conditions, because we will take different specific problems or specific examples, and we will take the boundary condition according to those problems or according to those examples, and try to find out psi, because if we can find out psi, we will be able to find out psi star, right? Now how to solve this equation? If you, although it looks it looks a little bit clumsy, but if we look carefully, it is not difficult to solve that equation. In fact, the mathematics was ready much before to solve such equation, and you know that mathematics. So you see, we can solve it by using separation of variable method. Okay, so what is that? So let me write it down once more. The Schrodinger equation. So this is the Schrodinger equation. We use separation of variable. Okay. I'm sorry, my handwriting is horrible. Primarily because of this screen, I can't write properly. Um, Separation of variable method. So what is separation of variable method? That you probably know. Just let me. So let's I'm assuming small psi and a small phi as capital psi xt. Okay. Now if I use that and put it in this, say this is equation 1 and this is equation 2. So if you put this here, you will get it. What we will get? H line square over 2m. Okay. Del 2 psi del x2 phi t plus ux small psi x phi t I h line psi x, and here we uh, will have phi t, right? Because psi x is independent of psi x and phi t is independent of each other. So we are basically, when we are taking derivative with respect to psi x, phi t will be outside, and similarly when we will take derivative of phi t, psi x will be outside. So we can divide dividing by psi x phi t. So we will get h line square over 2m 1 by psi x So you see, if you look carefully, okay, if you look carefully, this the left hand part is only function of space, okay, and the right hand part is function of time. So this part, okay, only space term is there, and this part only uh, it has time term over there, right? So this is function of space and this is function of time, right? Now, because you see here there is no time term and here there is no space term, right? So uh, we can uh, solve it, and so this equality condition is true if both sides must be equal to a constant, right? Because this is only space term is there, this is only time term is there, these two can equate, okay, or these two, this equality condition can only be valid if they are equal to a constant, okay. Now this IH line, IH line 1 by phi t del psi t, I mean del phi t over del t, this is nothing but, you see, this is nothing but energy, right? You remember, this is nothing but energy, because you see this left hand turn, this is kinetic energy and this is potential energy, right? And this is nothing but total energy, right? So this, although I am assuming, say this is a constant, these two are equal to a constant which is basically A, but this is nothing but the total energy, right? Now let's solve that time dependent part. Okay. So if you solve it, what you will get? You will get, oh, I missed, sorry, I sorry, um, yeah, no, it's okay. So I've taken this del dt over here, and the straightforward solution is this, okay? Or you can also write phi t is equal to e to the power I e over h line into t is the total energy, because this is nothing but total energy, right? Now, so this is my solution of my time dependent part, okay? What about the space dependent part? Space dependent part is this one, okay? And here also we can use that constant A and can rewrite that expression, right? So if I rewrite that expression, which will, so this is the solution of the time dependent part, and dependent part is, right? I have multiplied psi x, because you see the psi x was here, I have multiplied it psi x, so I am getting a psi x, okay? I am getting a psi x, right? So this is known as time independent Schrodinger equation. This particular equation is known as time independent Schrodinger equation because there is no time dependent part. Now the thing is, you will see that for different problems, what we are going to do, we are going to find out psi x, okay, and then we will multiply that with e to the power minus, we will multiply with this e to the power minus I over I into e over h line t, okay, because what is the general solution? General solution is psi x multiplied by phi t, right? That is the general solution. So we know phi t is this, phi t is this. All we have to do for a particular problem, applying boundary conditions, we will find out this from this formula we will find out psi x, okay? What is psi x using boundary conditions, right, for a particular problem. Now once we find out psi x, the capital psi x t, which is the wave function, that is nothing but psi x phi t, right? So phi t we already know, e to the power minus I e over h line t, so that we can multiply once we get psi x and get this capital psi x t, which is the main wave function, right? Now what we are going to do, we will take up two problems or two examples to see how psi x can be found out. Okay, one of the examples, I'm pretty sure probably you have done this before, maybe in your physics class somewhere, if quantum mechanics is covered in that. So one of the example we are trying to do here is known as 1D infinite square well or potential well. Okay, so that is the first example we are going to discuss. Now this, so as I said, our intention is to find out this small psi x, okay, for a particular problem. So once we find out the small psi x, we will be able to find out the capital psi xt, right? So let's see how we apply those boundary conditions to find out psi x. So one of the example we are now trying or looking at is 1D, one dimensional infinite square well or infinite potential well. So say this is my potential well, okay, potential well dimension is between x equal to 0 and x equal to L, and as it is infinite potential well, the potential barrier at the two sides of the well is infinity. Okay, in other words, the particle which is inside somewhere here, okay, for it this part is classically forbidden, these two parts are classically forbidden, right? So these two parts are classically forbidden, and we also, it is easy to say within this potential well the potential energy is zero because this is the single particle only present there, there is no other particle, and so there is no interaction of this particle or electron or whatever, okay, with any other thing. So the potential energy associated to this particle is free inside the potential well. So the potential energy associated with the particle is zero, right? There is no additional particle to whom it will interact. Okay, so the potential energy inside the potential well is zero. Okay, so we can write the boundary condition as potential energy is zero for within the potential well, and it is infinite otherwise, right? Now the particle is having mass m, okay, and it is completely free except at the ends x equal to 0 and x equal to L, because where there is infinite force to prevent it from escaping, right? Now the thing is, we can also write wave function associated with the particle. I'm only talking about space dependent part or time independent part. Okay, so the wave function associated with the particle uh, is 0. Okay, small psi x equal to 0 if we go less than x less than 0, or if we go x more than equal to L. Okay, so that is 0 because the particle can't go here and can't go here because there is infinite potential barrier. Okay. Now classically the particle will have a in a state of arbitrary, I mean if we try to solve from classical angle this particular problem, the particle will have arbitrary energy E, okay, and momentum you can say root over 2 me, I mean P is equal to root over Tme 2me, you can find out the speed and so on, okay, and the particle will move freely here, it can go bounce back, it can go here bounce back and so on and so forth. So that's the classical viewpoint. The particle might have any energy inside and the energy is continuous or any arbitrary energy inside the well, okay, and it will move freely here and there, it can bounce back from the wall, okay, and so on and so forth. Now uh, as there is no uh, additional particle inside, as there is no extra force inside, okay, we can, as I said, we can say that you can take ux equal to 0 inside the well. So we can rewrite the rewrite the rewrite uh, this time independent Schrodinger equation, okay, removing this particular term for this particular example. So if we remove this second term, okay, what will be the expression then? Right, because we are not considering that potential energy term. So h line square over 2m d2 psi x dx2 is equal to E psi x, right, because a is E, we already mentioned, right? A is E. Now the thing is we can solve this equation very easily, right? So we can write d2 psi dx2 is equal to minus 2m over h line square E psi x, okay, and this 2m over h line square can be shown is equal to k square, right, because you remember we have already discussed p is equal to h line k and p is equal to mv, which is nothing but 2m root over 2me, right. So you see here p over h line is nothing but k, right. If you look it carefully, it is not difficult to figure out this. So this is nothing but, you can write in the form of k square, right. Of course there is a negative sign. So what is the general solution of this? A sin kx plus b cos kx, right, this is the general solution. If you remember how to solve this kind of expression, you will get this, right. This standard, very standard basic differential equation. So it will give you psi x equal to a sin kx plus b cos kx, where a and b are arbitrary constants. So these are arbitrary constants, and these constants you can find out from using the boundary condition, right. So you see we have already talked about boundary condition. Psi is 0 because the potential barrier height is infinite. So at if we take x equal to 0, you see this a sin kx term will be 0, okay. So if you put this here, so you will get a sine 0 plus b cos 0, okay, equal to 0. So in other words, it will give you b equal to 0, right? b cos 0, that means b, because cos 0 equal to 1, so b, it will give you b equal to 0, right? If we use this, the second part, okay, we use this, that means a sine kl equal to 0, right? Because we have already found out b equal to 0. So all it remains a cos a sine kx, because b equal to 0. So psi x is equal to a sine kx, and if we say x equal to l, okay, if we use this condition, so a sine kl equal to 0, right? Now a can't be 0, because if you put a equal to 0, that will make things trivial, right? Then it will be like both a equal to 0 and b equal to 0. So it will give you a trivial solution. So a can't be 0. So we can't consider from this expression, because a can be 0 is a possibility, right? Because a multiplied by sine k equal to 0. So a can be 0, right? But a can't be 0 here, because we have already found that b equal to 0, right? So if a equal to 0 and b equal to 0 both are 0, then it will give you a trivial solution. So we can't accept a equal to 0. We can't also accept kl equal to 0. That also we can't accept, right? Because again, if kl equal to 0, that will give you trivial solution. So kl equal to plus minus n pi, kl equal to plus minus n pi, where n can't be 0, right? Now the thing is, this negative sign doesn't carry any extra thing, because you see sine minus theta is equal to minus sine theta. So that means this negative sign you can you can absorb within this constant a. So all we are left with uh, is a solution where I am just, the popular way to represent it is, sorry, where n equal to 1, 2, 3 and so on, because we are not bothered about the negative terms, because negative term can be taken care of inside a, okay. And in the positive term also we can't take n equal to 0, we can take n equal to 1, 2, 3 etc. And this k, so k I am now writing k suffix n. So only specific values of k are possible, right? So k becomes quantized. You see, the popular way to tell it, that k becomes quantized due to this boundary condition, right? What is the boundary condition? That psi x equal to 0 and psi x equal to l, the psi will be 0, okay, at x equal to 0 and x equal to l. Because of this boundary condition, the k becomes quantized, okay. Now if k is quantized, that means energy is also quantized. Why? Because you remember, we have already found that kn, I mean the k is 2me over h line, right? K, we found that 2me over h line in somewhere here. You see, k is 2me over h line. Now if k is quantized, energy is also quantized, so that is why I am writing E suffix n, right? So this En, right, can be written as h line square k square, I mean k suffix n over 2m, right? can put the value of k as n pi over L. Okay, so n square pi square over L square. So this is the usual popular expression of energy of the particle inside that infinite potential well. Okay, so the point I would like to emphasize here, unlike the classical case, in the classical case the particle can have any energy inside the potential well. I mean, it can't have infinite energy, but it can have any energy inside that potential well. But here the quantum mechanics from Schrodinger equation telling us that the particle can't have any energy like in the classical case. It can have only some specified energy, okay, because A will have 1, 2, 3, 4 and so on. So this specific energy of the particle is only possible. Okay, so the energy will not be continuous in the infinite potential well. This particle can have only specific energy. Okay, specific allotted values. Now the thing is, so we now see that psi x, which is a sine kx, k here I am writing k suffix n x, right? So that's the solution of the spatial part or the time independent part. So that's the solution. A sine k n k suffix. In fact, I put a n sine k n x. Okay, n is so a suffix n sine k suffix n x. So that's the solution. Now the thing is, we need to find out the value of a or a suffix n, right? Because that's a coefficient, right? So this coefficient, so this a is nothing to do with the way. I think I should have put a different symbol, because this has nothing to do with this a. You see, these are different. So this is I mean, this is, you put e psi x, probably that will be better. Okay, you put e psi x. Now the thing is, this a which I was describing earlier is nothing to do with solution a here. Okay, please remember this a and that a is different, right? Now the thing is, this a we have to find out. I mean, I am putting a n, anticipating this a might be quantized as well. That I don't know, I have to find it out, but we have to find the value of this coefficient. Okay, a n, a suffix n. So how to find out this value of this coefficient? By using the probability density, right? We know what is, we know how to find out probability. You remember? So psi star x dx equal to 1, right? So in fact we should write 0 to L, okay, psi star x dx equal to 1, because the particle surely should be there inside this potential well, right? The particle is surely there. So the probability of finding the particle inside this well is 1, right? So instead of integrating it from minus infinity to plus infinity, we should integrate it from 0 to L. Okay. So if you write psi x and psi star x, okay, because we know this, what is psi x? Psi x is a sine, you remember, a n sine k n x, that is your psi x. So you put that, okay, you will end up with n square sine square n pi x over L dx equal to 1, okay, because kn is n pi over L, so n pi x over L dx is equal to 1, right? So you can, I'm pretty sure you will be able to integrate this expression. Okay, you remember cos 2 theta is equal to 1 minus 2 sine square theta, so you can use that. Okay, and find out um, this integration. Okay, I mean I can do 1. So this is 1 minus, so you will get 2 sine square theta, so you will have like 2 sine square theta equal to 1 minus cos 2 theta, right? 2 sine square theta is equal to 1 minus cos 2 theta. So sine square theta is equal to half minus half cos 2 theta. So if you use this here, okay, you will be able to integrate it. So half will give you x over 2, right? If you integrate, and this half cos 2 theta, okay, theta is, what is theta? N pi x over L, so that's basically your theta. So if you check carefully, so another 2 term will come out. There is 2 term here, another 2 term will come out because cos 2 theta, another 2 term will come out, so it will be L4, and theta contains n pi over L, so that L over n pi, this term will come out, right? So I hope you can follow this what I am writing. So, and cos will, when you integrate, it will give you sine, so 0 to L is equal to 1, and you do that, you will ultimately get an equal to root over 2L, root over root 2 over L, okay, root 2 over L. Now, so you see an is independent of n, so we can write a instead of a. Okay, so what is the solution? What is the solution of the time independent part? Root over 2L sine n pi x over L. So that's the solution, because you remember we found out, so this was the solution, a sine kn x, kn is n pi over L, right? And a we found out root 2 over L. So root 2 over L sine kn x, kn is n pi over L x. Okay, so that's the solution. Okay, so you remember how to find out psi xt. Okay, that is psi x phi t, right? Psi x you found out from here. What is phi t? Phi t, you remember we found out e to the power minus I e over h line t. You remember? Just let me go back there. Yeah. So this is my phi t. Okay. Phi t is e to the power minus I. Okay. E over h line t. So you just multiply psi x and phi t. Total solution. Okay. So this is the psi x, and phi t we already know. If you multiply these two, you will get the total wave function. Now let me just discuss a bit more, because we said we are interested in finding out probability of finding the particle, right? So probability density we are interested in. So before going here, let me show you how to find out probability. Okay, so the way usually we represent this psi x, you see it is an oscillatory function, right? It has like sine n pi over Lx. So you can plot this. You can plot this. Okay. So say this is x equal to 0, this is x equal to L, and for n equal to 1, how will be the waveform for n equal to 1? So for n equal to 1, it will be root 2 over L sine pi x over n, right? N equal to 1. So we can plot this, okay, for n equal to 2. So this is for n equal to 1. So I am plotting the waveform from the solution itself, okay. For n equal to 2, what will happen? So this is for n equal to 2. You see amplitude will remain the same. Okay, when you started drawing n equal to 1, 2, 3 for these waveforms, okay, you see amplitude will remain the same. Why? Because A is nothing but root 2 over L. So A remains constant. So amplitude of the wave remains constant. So whatever n equal to 1, 2, 3, 4, whatever waveform you draw, okay, between these two walls, the amplitude will remain the same. So this is in one half. What about the other half? The other half, we will have the waveform like this. I mean, it is straightforward, but let me just control. I lost my control over the over the. Okay, now it is. So what about the? So this is in one half. What about other half? Right? So this dotted line in blue is in the other half, right? Other half of the period. Okay. So dotted line in the blue is represents the other half, and the red line is another half. Okay. So this way you can draw n equal to 1, n equal to 2, n equal to 3, and so on, the waveforms. Now the thing is, you note, this is the basically the spatial part, right? This is the spatial part, and you see this is nothing but the wave look like, the waves look like waves on a string, right, of length L. Okay, you remember we draw string waveform. Did I draw it? I can't remember. Yeah, probably at the beginning we draw string waveform where it was here. You see standing wave, uh, it will generate a standing wave. You see uh, this is in one half, it will have in another half, it will be like this, right. So this is in the string, this is a standing wave, moving backward and forward. In the same fashion, in here also, the it will generate a standing wave. The infinite potential well will generate a standing wave. Okay. Now this standing wave will move backward and forward, and this is the waveform looks like. You can also, there is a temporal part, obviously. Okay, so that makes the oscillation, and you can, and as I said, all the waves will have the same amplitude, and we often can draw the waveform superimposed in energy diagram as well. So we can draw the waveform in this fashion also. This is another way of representing it. Uh, so x equal to 0, x equal to L. Okay, so say this is my n equal to 1. So this is energy diagram, n equal to 1. Okay, this is my n equal to 1. What is, so that will give you E1, right? H line square pi square over 2ml square, right? You remember we found out E suffix n. We can draw n equal to 2 also. For n equal to 2, this will give you E2. E2 will be 4E1, right? You put it, value of n, you will get 4E1. So that this will give you this n equal to 3 and so on, right? Okay, so I think I will stop it here today. Tomorrow we are going to discuss probability density, how to find out probability density of this waveform, okay, or of the particle which is inside this infinite potential well, and we will make some conclusion of these observations, okay. Then what we will do, we will find out the if the potential well is finite instead of infinite, what will happen, okay. If the potential well is finite, then what will happen as far as the psi x is concerned, that we will look at in the tomorrow's class. Now couple of things I would like to mention. One is, have you done the have you have you solved any of the problems I shared with you, a problem file in the MS Team? Did you manage to look at it? Nobody? I think I've shared it, right?
Yes, sir.
Yeah, so so uh, you need to look at it, uh, try to solve problems associated with the part I have already covered, okay. So this de Broglie part, this initial quantum mechanics part, the IC roadmap part, HEMT, HBT, if there are problems in there, okay, you um, you try to solve those. Where did I put? Um, yeah, so this is the mathematical problem, okay. Uh, why it becomes blue? Why can't I open it? I don't know why can't I open it. Um, Let me see if I can find out. Uh, where it is? Yeah, probably this one. So I've given some problems. Some of the things is not covered, so don't bother about doing those. Okay, for the time being. For example, number 2 uh, is using photoelectric effect. Uh, this is again using de Broglie equation. Okay, uh, these two is there. Uh, this is again de Broglie wavelength. Using de Broglie wavelength, you try this again. This is the one which I am talking now. I mean the potential well, okay, uh, and so on. So these problems, you try that. You try this particular problem. This is solved in Z's book. If someone has this book, maybe these books are available online also. Semiconductor device, this book. If you open the HEMT chapter or MOSFET chapter, there probably it is mentioned as MOSFET. You will get this problem. It is solved over there. Okay, because this problem is given 2-3 times in last several years, last 6-7 years it was given. So I collected it and put it here. Okay, so you try these problems, because in the exam some problems will be there, okay, and some theoretical part will be there. So I am thinking to take your exam uh, on 21st. How about that?
Sir, we have
21st.
an exam on 21st.
You have exam on 21st.
Yes, sir.
Uh, um, okay, but exam is not from 8 to 10, right? Will you not be able to give exam? Otherwise, because what about 22nd? Because 22nd it is like only one period. I mean, that's fine. We will not have exam more than say 45 minutes or so. So what about 22nd?
Yes, sir. 22nd is fine.
Okay, so 22nd, then we can uh, mm, we will have exam on 22nd. Okay, please mark in your calendar. So whatever I have covered, I will cover till tomorrow will be in the syllabus. Okay, so we will have a HEMT, HBT, IC roadmap, FinFET, right? And then we will have this quantum mechanics part until tomorrow. Okay, so please,
Sir, how
please.
many questions will be there?
I don't know. I haven't prepared the questions, but I will make the questions in such a way so that you should be able to write it in 45 minutes, 45 to 50 minutes. So you will have like 10 minutes buffer, 10 to 15 minutes buffer. The way I look at it is like you write the questions, okay, take a snapshot and upload it in MS Team. So I will create an assignment folder you or assignment section. You upload it in that assignment section like we did for the assignment part, right? So so I will give you a time, but do not scan and send to email your answer, because I have seen this before, and it overflows my, it will overflow my this thing, my email. Okay, because my email hardly has any space left. So if you start sending these large files, it will overflow it. So the way I will prepare the questions, the question will be yeah, very brief. You write the answer brief and to the point. Don't start describing and writing for 2-3 marks question. You don't write it for 2 page. So then you will not be able to finish it. But the questions will be brief to the point, and you write answers accordingly. Okay, there will be some problems. So maybe 50-50 maybe problem and 50% maybe theory. Okay, but theories are very small, like half page answered, few lines answered. I will not give you question where you have to write 2 page. Okay, so that's not my intention. So you don't do that, then you will not be able to finish. So the way I will prepare it, that you should be able to finish it in 45 minutes. Take snapshot. You will get 10 minutes, roughly 10 to 15 minutes, so that between 12 and 1 we should be able to finish. Maximum 110. That I will see after making the question. I will see how long it takes, and accordingly I will give you the time. Okay, so to prepare it, and best of luck. Okay, any doubt in today's this thing, today's uh, whatever we have discussed? Do you have any doubt? Because I don't know how fast I was. These are little bit difficult portions, but I don't have time to go through a lot of other things, as I said, Heisenberg's uncertainty principle and all that. But whatever I am discussing will be in the syllabus. I will not give questions outside this, what I am discussing. Okay. So if you have any doubt, you can ask me now. Otherwise, I will close the session and then we will start tomorrow again. So tomorrow we will finish this part. We will discuss the finite potential well and compare the solutions what I am getting in infinite potential well and finite potential well. And please try to solve the problems I am given. I have given in the problem sheet. The problems will be not exactly same, but you can expect similar problems. Okay, so please solve those. Um, those are not difficult, but you should solve it before appearing for the exam. I think there are 5-6 problems, which is what I have covered so far, so it should not take much long. But if you have problem with this hem thing, you let me know tomorrow, then I will send you the solution from the Z's book. If you don't find it and don't able to do it, because that's not straightforward, the hemmed problem, then I will scan it and upload it in the image team, the solution of the hemmed problem. Okay. Other problems I think pretty straightforward, or I mean by straightforward I mean by using the formula. Okay, the known formulas, the formulas we have discussed, that is using that. So those are pretty straightforward, but you should remember the units and all that, the electron volt, arc, joule, all those units you should be very careful. Okay. Okay, no doubt. You don't have any doubt? Right. So the way I am covering, is it understandable or I am going fast?
No, sir, it's fine, sir.
Okay, right. Okay, so thank you very much for your time. So then see you tomorrow. Okay.